can instantiate a number of processes or threads to run multiple jobs that it's supposed to do. But if let's say they need to interact with one another or they share information, then you will need this inter-process communication. It's basically communication between processes or threads. Okay. Here, process and thread is assumed to be the same. Actually, there are slight differences between them, but we assume that they're the same. Okay, for the moment. Now, what we're going to cover is the inter-process communication, what it is all about, and then we go on into how it is used in real world, especially when we do distributed system. We will have client server and peer-to-peer system, and here you can see that they actually run processes either on the same computer or different computer. In distributed manner, it will be a different computer, and of course it's also inter-process communication as well, except that it's not on the same computer, it's on different computers. Okay, and we will use a similar technique in order to communicate between them. Okay, now if it is on the computer alone, we can use it. We can communicate using memory. If it is not, we have to use communication media like Ethernet, Wi-Fi, or whatever in order to transport the data across. But of course, along the way, we need to learn a little bit about TCP/IP, UDP. I believe all of you have learned networking before, right? Have you learned networking? Networking subject. Only this group. How about the rest? All have learned networking. Okay, so basically it's something what you have learned before. Maybe networking you learn about routers, switches and all that, right? But here we're going to learn about how to, not to set up the routers or switches. We want to create communication socket using this TCP/IP in order to send and receive data over the network. Okay, so that will involve sockets. This one is communication through communication media, and the next one is pipe. Pipe is something to do with communication between processes on the same computer without using networking. Okay, and also we're going to look into different ways to communicate. Okay, we want to look at message passing. Here is it talk about issues. Actually, it's not issue. It's communication techniques. We got message passing, basically deal with data, and then we can also invoke job to be done on computer, okay, remotely, and we use this RPC and RMI. And then how do you bind all together? That means how do you make the distributed system work using this low-level communication protocol. We're going to look a little bit about middleware. Actually, it's only one slide. Most of the time, we will be using middleware rather than low-level, unless you are doing low-level programming. Okay, inter-process communication is important if you are cooperating. So you got two different kind of processes that's running, execute concurrently or in parallel. Either the processes run independently, they don't communicate with one another, they don't share data. So this is the simplest one. If independent processes, you do not need inter-process communication, and you will not have race condition, you will not have anything, and you can run in parallel. This is the best and the nicest one. But in real world, it is not always the case. Okay? In real world, normally when we create multiple processes, they need to communicate with one another. So this kind of work together, we call cooperating processes. Okay, so independent processes, they work independently. There are multiple processes that is instantiated. They are work independently and they don't communicate. Cooperating means they need to communicate in order to be able to work together. Okay. So here you only use this word run concurrently. Actually, it also applies to parallel computing as well. So run concurrently or run in parallel, right? They mean the same in this case here. That means you need to also create processes, even though they run concurrently. You have to create processes, If you run in parallel, you also have to create processes. There's no difference there. Okay, the only difference is how they are executed. Okay, concurrently means a single core, they multitask using the single core. Of course, you got multiple cores, all of them run concurrently. That means all of them run processes in a single core, and they have to task switch. Okay, they have to use the CPU with a timer, like what I mentioned to you on the board, where they task switch on one another. Okay, if you run in parallel, you don't need this task switching. Okay, you just assign one process to one core, and they just happily use the core and use it as for itself. Okay, it does not need to share with anyone. Okay, so what do we need to communicate? Why does the process needs to communicate? There's an advantage for doing that. First thing is you have a situation where you need to share the information. So you got information sharing. Let's say you have a file that you open, and then you share this information. Okay, one example, maybe this is quite abstract, you won't be able to understand the importance of it. Let's say I try to play a video, okay, play a video, and of course you can use single process where it read from the file, it decompress it, because video are all compressed, right? You have to decompress the images frame by frame and then display on the screen. Okay, so that is using a single core. But nowadays we have a computer with multiple cores, right? So what we can do is we can expedite. That means we make it faster. If let's say, for example, high resolution, maybe single core is going to be quite slow. So high definition, let's say 8K screen, there are quite a lot of pixels there. So what you can do is you can chop down the screen. Let's say this screen here, you can chop down into multiple squares, okay, multiple segments, and each segment needs to decompress its own segment and then display on the screen. And they can do it at once. Okay, if you have multiple parallel cores that is running, you can display at the same time. And in this case here, each core actually needs to decompress the image, right? Where does the image come from? The image comes from the file. Do you expect each core to open the file? Let's say you got GPU run 2,000, maybe 1,000 cores at one time. If you expect every core to open up the file, it's going to be slow, isn't it? Everybody is actually opening the file and then read the file. It will be better that one core open the file and then they share. So the core will actually disseminate. Okay, you are doing that on the top left, so that image from this file I'll send to you. Okay, and then the other track is doing the other tiles or the other segment. So you receive the part of the data that it needs to decompress. So in this case here, there's information sharing from the single core that is reading the file to the rest of the core that needs to decompress and display on the screen. Okay, so that is information sharing. And of course, running a process in parallel while doing cooperation job like what I mentioned to you, it's going to speed up the computation, right? Because you can split the tasks into multiple tasks, but everyone is actually doing decompression, just that they are doing everything together at the same time. Okay, so you can have a speed up in computation. And another thing is, okay, this one is slightly different. Modularity is something to do with how we think and how we design our system. Let's say, for example, now I'm talking about slightly different things. I'm not going to use the video decompression. Let's say we have modular programming where we have one system is actually, okay, let's say video again, but we use browser. Okay, we use browser to watch video streaming, let's say. Yeah? So now we have browser itself run one process, okay, because it has to create connection to the server and then get the data stream. So data stream is coming from the server, it handles that. It doesn't do any video decompression, it just stream the data from the server to the PC. Okay, it just handles that. So that is one process. And once it receives the data in chunks, because stream you actually receive block by block, right? After you receive one chunk of data, you pass to another task or another process. This process is just decompressing only. Okay, it does not do the networking. It only knows how to decompress. So once it decompress, it passes to the next process. The process will display on the screen. So right now you got 3 processes there. They are helping one another. Okay, one is the browser, just doing the streaming. It needs to know how to do internet connection and also data streaming. That means it needs to know networking protocol. The next one is only doing decompression. So it needs to know the MPEG protocol, how to decompress it. And then the other one is displaying on the screen. That process is just display on the screen only. And its job is, so it needs to know how to communicate with the monitor and then display on the screen. So there are 3 different jobs, and they're all modular, right? And this kind of modular programming make it simpler, right? For example, I can ask one programmer who is very good in networking. He only work on the browser side. The other person who is doing video, he's doing only one process. The other one is only monitor. Maybe he's good in hardware. He knows how to communicate with the monitor, and he's doing that. So it's modular programming, and it makes programming much simpler and more well organized. Okay, so process cooperation like this is useful in that sense. Okay, so that's modularity, and the other one is convenience. Convenience for the user to perform the task at the same time. This is more of the user side. The first 3 is more of the processes. Okay, the last one is more of the user experience. Okay, so let's say you got processes running at the same time. Let's say you do editing and then you want to switch to browser. You don't have to close the program and then open the new program. This is more of the convenience, right? So you want to have multitasking program running on your computer is because of that. That's why we all use multitasking operating system. We don't use DOS anymore. DOS is it's not multitasking. If I want to use database, I have to run database. Once you finish, you have to close that database. Then you have to open another program in order to do your other job. Okay, that's what happened in the past. If you have a non-multitasking OS. Okay, inter-process communication, or short term, we call IPC, and this also applies to thread as well. Even though here we only discuss about process, but we can assume that thread is the same as process. So whatever that applies to process also applies to thread as well. So inter-thread communication or inter-process communication is the same thing. But the more common word that we use is actually inter-process communication. Okay, and there are 2 mechanisms, fundamental models that we use. The first one is message passing communication model. The other one is shared memory communication model. Okay, here is how it looks like. In the message passing, here you see there are multiple processes that is running. On the right hand side is also multiple processes. On the left hand side, it shows to you how message passing works. Okay, on the right hand side, how shared memory works. Okay, why interprocess has 2? The B one actually more useful, especially for computer running multiple processes on a single computer. Okay, we want to use shared memory because it's fast. Okay, later you see why is it fast. But let's say your process run on different computer. In different computer, you cannot share memory, right? Because each computer has its own memory. In that case, you have to send the message. That's why you have message passing. That's why there are 2 different types of IPC. Okay. Now you can also use IPC. You can also use message passing for even though the processes run on the same computer. It doesn't mean that if your process run on a single computer, you have to use shared memory. No, you can use message passing as well. Okay, but not the other way around. That means if I have processes that running on different computer, I cannot use shared memory to inter-process communicate. I have to use message passing. Okay, but on processes running on the same computer, you can use both. Okay, now if let's say you here actually show to you that it actually run on the same computer, suppose. So it has message that it needs to send. So what it does is it has to create that message first and send it over. It's not shown here. be shown it as an arrow like that. Okay, that message maybe travel across the network and then come back. Okay, so you have to create a copy. So this is one copy. There's another copy that is physically traveling, electrically traveling, or maybe optically traveling through the communication media, and then come back to the same computer or different computer maybe. And you can see that how many copy there? You got 1 copy, 2 copy, and 3 copy. Okay, the third copy is actually not in the memory. Actually, it's traveling in the medium. Okay, either Wi-Fi, that means wireless, electrically, if let's say use electrical signal, or optically, let's say if you are using the optical fiber optics. Okay, so you got 3 copies there, and this is going to be slow because you have to create the copy, send, and then receive, and have another copy there. And another thing is you have to use a lot of memory. Okay, on a separate computer, then it's fine, you have no choice, right? But on the same computer, you have 2 copies there. That 2 copies use up memory. Okay, so you can use message passing on a single computer, but it's not advisable. Okay, if let's say, why do you need to do this? Maybe because you want to make your program. How to say? You want to make your program so that it can be used either on the process running on the same computer or different computer. You have to change the code, right? I write only one code, message passing. Then that code can be used for processes running on the same computer or different computer. I don't have to change the code. Okay? But if I use shared memory, then I have to change the code if I want to do distributed communication, because it will not be applicable for distributed system for the shared memory. Okay? So message passing has its own goodness as well, especially when you know that initially when you design, you use on a single computer, but in the future you know that you're going to do distributed systems, so you don't have to rewrite your code. You use the same code and it will work the same. Okay? Now it will be kind of funny, since it has to use networking in order to transmit the data, right? But if the process is running on the same computer, how does the transmission go? Actually, your Ethernet has a loopback. Loopback means it will loop back. Okay, you send to the internet. Actually, it doesn't send the signal to the wire. No, it actually loop back to your computer. So we use loopback, and it's slightly faster. It is slow still, but it's slightly faster than really transmitting and then receiving. Okay, so we can use message passing on a single computer. Just that you use loopback, you don't have to know that. Whenever it sees the same address, automatically you use loopback. Okay, so you don't have to configure it. Okay, how about the shared memory? The shared memory, as I said before, is fast because you are sharing your memory. But this one will not be applicable for distributed system. So your process need to run on the same computer, and that computer need to be shared memory. Okay. Now, when I say same computer, it doesn't mean same processor. It can be multiple processor. For example, IBM create mainframe. The mainframe can have 100 processors, but these 100 processors might share the same memory. Okay, of course, it's not 100, and normally it's only 8, 16, or 32, or maybe 64 at most. Okay, because if you have too many processors, they're sharing the same memory, it can be slow. Okay, so normally the size is quite small. Let's say 32 cores. 32 cores has one big memory that they share. Okay, so it can be multiple processor, but it's running on the same computer. Your computer has multiple processor. Processor and core is different. One processor can have multiple cores. I'm talking about processor. Processor is different chip. Okay, so you can buy different Intel chip, for example. Let's say 32 chip, and then you put into your server, and your server will have 32 processor, and this processor will have shared memory. So with that shared memory, even though different processor, you can communicate. Okay, let's say process A run on the first processor, process B run on the second processor. They can use this shared memory. all these processors run on the same processor. They also use the shared memory as well. Okay, so this shared memory is only one copy. So what you do, let's say A want to pass the message to, or want to share the memory, that means pass that message. This data here, it doesn't make a copy and pass to process B. It actually pass the pointer. It just gives the pointer to process B, and now process B has that pointer. It can access that same shared memory. So once you put the data there, you don't have to do anything. You don't have to copy, just pass the address. The address is very short, right? So the communication here, or the way you communicate, is very fast compared to message passing. Okay, it's time consuming for the message passing, especially if you have to, the signal has to travel. But if let's say you have to travel through the network, your computer is separated quite far apart, you have no choice, okay? But of course, if let's say your process is running on the same computer, we prefer to use shared memory. Now, OMP that you learn in the lab is all using shared memory. Okay, in the future, I'm not sure whether they're going to change that or not, but at the moment, it's all shared memory because it assumes that the processors is running on the same computer. In practical 4 or 5, I can't remember which one, we're going to learn another way to do parallel computing is using another platform called MPI. MPI support both. It support message passing, it support shared memory. MPI stands for Message Passing Interface. The name itself already mentioned that it's message passing. So you can do parallel computing using this library or platform. And we are going to use, we can use message passing, we can use shared memory. But most of the time is message passing, okay? Because it does not assume that your process run on the same computer. So OMP, if you write the program, all your parallel computing process need to run on the same computer. When we move to MPI, we can use 3 or 4 computers, and then we make it as a cluster. Whenever we run the program, it will load balance. It can do this automatically. You can pass the message without you knowing it. You just write a program, a same program, as though as you run on the same computer, but behind the scene, it will do that. Okay, you will transport the data to another computer, process it, and then send it back. Okay, we will cover this in one of the chapter. One of the practical. Okay, how is it used? Okay, just now I mentioned to you is the concept. Now in real world it is used mostly in a client-server way. It uses distributed computing, of course, because you have a client that is us. For example, we use internet always, right? So the internet is accessing servers that is in remote area, and that will involve distributed computing. So basically, we are already using distributed computing, just that you're not aware. Okay, distributed computing. Once you use the web, you access browser, your browser or your web page, is already distributed computing. Okay, and of course, your client, which is your browser, is communicating with the server, which is sending the web page. Okay, so there are 2 processes at least that is running at the same time. Okay, the server is a process. You can think about one process that is running on the server computer, and it will do its own computation or services, and the client is requesting for the service. Okay, the client does not do the job, but it requests for the service. For example, your browser it does not do any operation. Let's say, for example, you're purchasing a product, let's say from Shopee. All the purchase transaction and all that is done by the server. On your screen, it's just showing you the transaction has been done. Okay, so of course your client needs to send the correct messages in order to do the correct operation. But then your client is basically just sending the request only. Okay, your server is the one that is doing the job. So client-server model is okay. The client usually is normally associated to a human. That's why you call client. Okay, so your computer that is serving or facing the customer or the user is the one that we call client. The server is the one that is doing all the work. Normally is the backend. Okay, this is how it looks like. You can have one server that is serving multiple clients, and all of them need to make connection. And this client server, of course, it has to do TCP IP. It has to initiate the protocol using the socket, most probably. Okay, and then the connection is private among all of them. Okay, let's say this connection 1 is only between A and S. Okay, connection 2 belongs to S and B. It's not shared. These are independent. Okay, and the server is allowed to have many clients, but client normally we have only one server. Of course, the browser you can open multiple tabs, and each tab is communicating with different server. Okay. Okay, this is one example, email example. So you got an email client requesting the message, email from the email server. Of course, we can think about. I believe all of us use email services like Gmail, Hotmail, and all that, right? So everything actually is stored inside the server. Okay, in the past, or maybe when you go to the company, they prefer not to use, they have their own company email. Your own company email will have its own server, is maybe running, or the location of it is inside the building itself. If let's say they don't buy cloud computing service, they serve their own. Like for example, in the past we have our own email server. We don't use it anymore. All of us use Gmail, right? So CITC decided to change. Last time we have email server, and the email server always have problem. Whenever there's any power disruption, even though we are outside, we cannot use it. Okay, sometimes they shut down because they want to do maintenance. Right? We cannot use it from outside. So we complain always. So right now they move to Gmail. Because Gmail, they guarantee us 99.99999% uptime. Okay, so it's much better. Okay, so you can have this kind of email. Maybe in the future, or when you go to the company, they will move to cloud computing services. But there are still companies that host their email server on their own premise. Okay, maybe for privacy reason, because when you go to the cloud, they don't trust. But of course, Amazon will tell the customer, we don't worry, because we will not peep into your email. We will not steal the information. So it's based on trust. Okay. Last time I used to work with a very big software company. I think they are the 14th largest company. They use their own server. Okay, so we were given, because I work on the project, so they give me an account. They treat me like their employee. So I have their own email, and we have to use their server. So this is one example. Okay, so your email client is going to ask the email from the server so that you can display it. Okay, and this email server will get the information, or maybe store the email inside the database. Right? So you have all the steps shown here. I will not go through it. Now the model that I showed to you just now is a simplistic idea of the implementation, but most of the time I think this is more realistic. Okay, the server is not only one server, there are multiple servers. Here show to you 2 servers. Okay, and then you got two clients. Now why you have several servers? Remember I mentioned to you modularity just now. Here we see that they are using modularity to run or solve the problem. One process is only handle the database, so this database server. The other one is doing authentication. Do you know what the meaning of authentication? Authenticate means try to find whether you are the rightful person who you claim you are. Okay, let's say for example I go to the entrance there, right? How do I identify myself? Maybe I use my card. Okay, because if let's say I use my card, then that card is associated to me, so they know that I'm authorized to enter. Okay, of course you say card is not secure. Maybe we can use thumbprint, right? We can put thumbprint on the digital thumbprint reader to access. Okay, so that is how we authenticate. The system authenticate me as a rightful person to enter into the compound. Let's say TAYMT, the same thing as you. But of course here we don't have so strict kind of security. But when we talk about computers, we have to do authentication always. Okay, especially when you do transaction, which costs a lot of money, and also information. You don't want to leak your information. You need to have authentication in place. Otherwise, people can come in and steal your information or delete your information. Okay, or maybe do illegal transaction and you lose money. You don't want that, right? So authentication is a process running on another server, and it knows how to authenticate. It doesn't know how to do database. So if let's say client process A try to access the database server do not know whether this guy is authorized to use the data or not, right? So it will ask authentication server to help. Okay, so first thing you ask the client A, okay, show me your ID, right? And then you relay this information or make authentication requests from the authentication server. The authentication server, of course, has its own database. You check whether this person is the rightful person and who he claims he is. Okay, and then you will send a message, request accepted, to the database server. So the database server will have to trust. You have to trust this authentication server. And once you receive this acknowledgement, then it will allow process A to proceed to use the data. Okay. Now the message that is sent back by the authentication server not only just approve, it can be maybe privileged as well. For example, CEO maybe have a better privilege than normal user, right? So it will send also some kind of privilege, whether you can access that particular database or not. Let's say, for example, HR, they're able to access information about the all the customers' information, but you cannot access that, okay? Because if you're able to access, you're able to steal the information and sell, right? Because they don't trust you. Okay, only HR is able to access this information. So any HR personnel, okay, when it authenticates, okay, you have that privilege, you can access certain part of the database where others cannot access. Okay. Okay, this is another situation. Just now is a situation where the request is accepted, that means authenticate successfully. The second one is the request denied because and it refused the service because the client B is actually failed to be authenticated. That means it failed to authenticate this is the rightful person to use. Okay, so that is client and server. I'm going to skip this for a while because this one actually not supposed to be there, but right, I think it's supposed to be after this. I'm going to go to here first before I go back. So just now it's client server. Now we look at peer-to-peer kind of model. Client and server, the server is the one that serves. It doesn't use the data, it serves the client. The client is the one that requests for the service. Okay, it receives the data. So there is a distinction between these two. Okay. How about peer-to-peer? In the peer-to-peer, they operate in equal standing. That means there's no client and server. The peer is both client and server at the same time. Okay. And how does it work? Okay, let's take one example. File sharing. I believe some of you use, or maybe all of you use file sharing software. Maybe BitTorrent. Do you use BitTorrent? Or maybe something of the past already. Right now, nobody uses BitTorrent. Anybody use BitTorrent yet? You use BitTorrent. How about the rest? Nobody use BitTorrent. Oh, some use BitTorrent. Oh, okay. I see quite a number of you use BitTorrent. Okay, BitTorrent is file sharing. Of course, you can share illegal materials. You can also share legal material as well. But most of the time, I think BitTorrent, they share illegal materials. For example, new movies come out. right? And then people start to share already inside BitTorrent. Maybe they capture it from the cinema and then start to share the video. Or maybe there's new song coming out and then it gets shared. Okay? Actually, BitTorrent, it was a derivation of a software called Napster. I'm not sure whether you all heard of Napster before. Now no more. Napster is actually developed by a youngster. Maybe I'm not sure how old he is. I think he's a teenager. During that time, we used client and server, and then he came up with this idea. He said, if I want to overcome this file sharing, because at that time, company like Sony, they start to charge quite a lot of money, especially when you have video. And then he was thinking about how to bypass this. Okay, and he does not have money to buy a server, so he's thinking of this peer-to-peer, because peer-to-peer, it means that if you want to share, you yourself need to participate in serving others as well. The idea is that, okay? Because he is a teenager, he does not have money, so he said, okay, if you want to share, then we have to collaborate. If I share with you, you have that copy. If somebody else needs it, you also have to share that copy with others. Okay, so the idea is this: if you use the service, you have to share. Okay, you have to share some of your data that you collected. Okay, but peer-to-peer works in non-centralized. Of course, Napster initially when it worked, because the design it was supposed to be simple, it's a centralized system. But then BitTorrent is actually non-centralized. Non-centralized means everybody has its own authority to do certain decision. Okay. So how does it work? If let's say one peer, it's not described here. Second point, third point, the fourth point, we will skip that. That is not important. The more important is what I'm going to explain to you, how peer-to-peer works. So we got a number of processes that is sharing data. Maybe I draw on here better. Okay, let's say for example, let's say this guy has a lot of materials. Okay, file A, file B, file C, let's say. Okay, let's show it all the files, maybe different size than this. Okay, let's say this is node 1, node 2, node 3, node 4, node 5. Okay, and suppose this node here, okay, once the file this file B, okay, it will request. Okay, so this will be the server temporary. It's a peer, but it acts like a server. So it sends the file because he's the only owner. So the only source that you can find this file B is from this node. Okay, so eventually this guy will have file D as well. Okay. Now let's say node 5 also one file B as well. Okay, so of course there is a way to actually go and find who has file B because it's non-centralized. BitTorrent is non-centralized. There's a technique to go and find it. If I want certain file, there is some information or metadata that is sent among all of them, so that if you ask for the file, they can quickly locate who actually has the file. So firstly, the peer-to-peer protocol will be able to identify. Say, oh, this guy has file B. Another guy also has file B. Now, this peer here will not only request from 3, it will request from both. Okay, so this guy will send maybe the first part. This guy will send the second part. Okay, he'll send. And eventually this guy will have file B. Okay, he will have the full one eventually. Okay, now why is this good? The reason is because if I split it this way, then this is not overloaded, right? Because right now I load balance. Okay, This is half, this is guy is half, and also can receive faster, right? Let's say this guy, okay, in big torrent you can throttle. Throttle means you reduce the bandwidth, okay? Reduce the bandwidth of upload. So I don't have to increase my bandwidth in order to serve you. I can share with you at low bandwidth. Because here I showed to you 2, but you can have 1,000. You can create 1,000 connection, and all of them are receiving file B. A little bit bandwidth from 3, a little bit from 4, a little bit from other peers. But eventually, I'll receive the file, and I'll receive very fast as well, because I get from all peers that have the file. Now, just now, this guy was a server, right? Temporarily, he was a server. This was a client receiving the file. But right now, this just now was a client. Right now, it become a server because it is serving this guy. So this peer is actually having 2 roles. It can be client, it can be server. Okay, the advantage is you can actually share the information much quicker. Okay, you don't need, this guy do not need to have very high speed bandwidth, no. Because all of them participate in helping Node 5 to receive the file. Okay, the same thing here. This guy already have file. Suppose this 1 need file B. Now it will request from 3. It requests from 4. It requests from 5 to get file B. So you can see here. Let's make some distinction. Peer-to-peer and client and server. Client and server, as you have more clients, everybody asks for file B, what is going to be the performance? The performance is going to go down or go up? How can go up? You have a lot of clients, client and server. Right now I'm talking about client and server. Every client asks from this one server for the same file. Can the server serve fast or slower as the number of clients increase? Slower, right? Correct or not? But how about peer-to-peer? More clients, more people have the file. Is it faster or slower? Faster. That means peer-to-peer actually scale better. Because if you have more clients, you're better. Is it right? Client and server model, no. If your server is only one server, of course you can have multiple servers, but suppose you have only one server. If your client increase, you have to scale, you have to increase your server equally. Otherwise you will not have, or you will suffer the bandwidth. Whereas in peer-to-peer, there's no such thing. As you increase, of course, everybody needs to have the data in order to speed up. If they don't share the same data, then there's no speed up also. Okay? So that is the reason why we have this peer-to-peer kind of timing. In fact, content delivery network also have some kind of similar. It is different protocol, but it shares some similarities. Okay, because the data is actually duplicate at multiple places. Okay, so meaning that if let's say Asia receive the movie, let's say receive movie, the content, the CDN is content delivery network, is also implementing something similar like this peer-to-peer. It's kind of peer-to-peer protocol. So it shares this data, and the data can be coming from different kind of content delivery network. Okay, to speed up or to help one another to deliver the data. So peer-to-peer, that is the advantage compared to client and server. Okay, especially when you share the data. Okay, as you have more peer that joins the network, then you'll start to have a better performance. Now you'll be wondering, how do they know who actually share the data? Actually, they have some kind of file. I'll just give you the concept, right? But they don't implement exactly like what I mentioned here. The concept is like this. They have a file, maybe a file name, and then they have some kind of information that is related to this file here. Okay, and this file here actually is enumerated according to alphabet maybe, okay, into the alphabet. And then what they do is they chop it down, okay, and then they will store this on some peer. Okay, even though I say peer-to-peer, they are all equal standing. Actually, it's not really true. Some peer has some kind of rank. Okay, the higher rank is the one that keep this metadata. Okay, so whenever I join, I will know who is the higher rank. So I communicate with the higher rank, and this higher rank can tell me who are the higher ranks people. So whenever I want for a file, my file name has certain name, right? So I will just tell, okay, my file name is this. Then they look it up in this table, see whether it falls here, here, or here. So if it falls here, it knows that who's the peer has this information. Then it will tell me where to go. Okay, so the idea is that. Okay, so this metadata is not the data that is sharing. It's just the name of the file that I want to get. Okay, and this name actually is like a name list. It tells who actually holds which information. Okay, we are not going to study that. I'm just giving you some idea how actually it locates the file quickly. Because when it comes to peer-to-peer, everything is distributed. There's no centralized server that keep track of the data. So you have to keep track this way. So they need to cooperate with one another. Communication is necessary. And the higher ranks need to communicate among themselves to share this information. So whenever a newcomer comes in, he asks for the information, he asks for this higher rank, and this higher rank will pinpoint who actually has it. And once it gets to that location, this peer here, the higher ranks peer, will know who is the subordinate peers that holds the data. So it has to go to this rank, and then you'll find the peer. So there are a lot of communication that happening. The protocol happening behind the scene is more complicated than the client server. So the implementation is hard, is tougher, but the advantage is better. Okay, client server, the implementation is not as complicated as this because you do not need to share all this information. You just go to the server. Okay, and the server will know because the server is the one that keep the data, right? So it should know where to get the information. Whereas peer-to-peer, the client have to go through a number of steps, have to go through a number of peers in order to find the information. Okay, but then roughly it works this way. Yeah. The metadata actually is small data indicating where the data is. It has association to the peer that hold the information. So the higher rank don't store the data. It's the subordinate peers that store the data. Okay, so the higher rank is the one that knows where the data is. Okay, so whenever the new peer that comes in, you ask this higher rank peer where the data is, and then the higher rank peer will tell the newcomer, okay, this peer has the data, you communicate with him. Okay, ask the information from him. So it's just like a person who acts like a directory, like a police, maybe a traffic police, maybe to redirect you to the correct person, or redirect you to the correct way to get your information that you want. Okay, and it relies on the metadata. Metadata is not the data; it's just maybe the file name associated to who. Okay, so it's going to be big, but it's handled by the higher rank. Now, how the higher rank is selected? Normally is selected based on the bandwidth. Okay, and also looking at how often it is up or how long it is up. Normally, if you stay on longer, you'll be elected as the higher rank. Okay, this is done automatically by the peer-to-peer protocol. You don't have to worry because it's already implemented as a protocol. You do not know whether maybe you can select as maybe there's an option for you to tell the system, I I am willing to become the higher rank. But you have to sacrifice your computation power in order to do this kind of job, to help others to disseminate information or share the information. Okay, peer-to-peer model is good, especially if you have a connectivity which is ad hoc. That means you have connection, then after that you destroy the connection. Okay, you create it and then you destroy it. You don't need it, all right? Okay, so just like here we have Ethernet wire cable, right? I cannot just say I want to remove it, no. But just to give you an analogy, I cannot just remove this wired cable. Okay, but then if I use Wi-Fi, I can come in, go out, come in, go out, right? So the network is actually formed as I come into the network, right? So I mean into the area, Wi-Fi area. So the same thing here. Client and server, just like the landline or the physical wiring of the network. Peer-to-peer is just like Wi-Fi. Okay, you come and go. Okay, you can come in, the connection is created. When you go, the connection is destroyed. So peer-to-peer also the same thing. For example, tree actually has all the file. It can actually stop functioning because this guy want to go to sleep. Maybe switch off his computer, right? When he switch off the computer, he's out already. Now you don't have to worry because the rest also carry file B. Okay. So the rest actually still have the file B. If a newcomer comes in, he still can share the file B, even though this guy go offline. Okay, it's unlike client server. If the client goes down, the data is off. You cannot get the data anymore. In peer-to-peer, any of these node, of course, he has to share first. If it goes out of service, you're still able to get the file. The file is still there because other nodes still has the file, right? So the connectivity is ad hoc. It doesn't matter because you can actually get the file from everybody else, right? So this ad hoc kind of connectivity can be spontaneous. That means it can come and go just like that, unplanned. You don't plan it because the fella can wake up anytime, right? And then get connected again at the time that is convenient to him. And it's unstructured. That means initially the network is like this. In another time, the connectivity is different. Maybe there's no connection here. And this guy maybe moved somewhere else. Maybe you are the peer-to-peer, one of the peer-to-peer, and you're using Wi-Fi and you're moving, right? So your connection actually keep on changing. And it doesn't matter because peer-to-peer can survive even though the connectivity is ad hoc. And it's not unstructured, unplanned, unstructured, and spontaneous. Okay, and of course here you have security issue. Let's say, for example, how do I identify myself? And of course, there is also security authentication system in place as well. You have to log in as well, right? To log in as claim who you are. And in this case here, everybody needs to trust one another. Once you get connected as a peer, then the other peer has to trust you. Meaning that whatever information that you share is the real data. Okay, it can be something like this. You are the person who are maybe a hacker, maybe, right? And you claim that this file is really file B, but actually it's not. Maybe it's virus there. You can share this. So this peer-to-peer cannot easily overcome. If you want to overcome, can, but it's not as easy as client and server. Because client and server, normally the server is owned by the company. In this peer-to-peer, we are using the resources by anybody who wants to become the peer or volunteer to become a peer, and we have to trust it, right? If the guy is a hacker, he wants to, let's say this is a program that is shared, let's say it's a one program and you can run on your system. I can inject virus inside there and claim that this file B is the original file and I share with you, right? If you receive that copy or that portion that has the virus, then your system is infected. That means if you run the program, you get infected. Okay? How it can be overcome actually, but how it is done, I'm not sure about BitTorrent. Maybe there's no such a system in place, but this is a real threat. Okay, especially when you have peer-to-peer and you are. That means um, if you use client and server, you need to make sure that you have enough capacity. That means you have to buy expensive equipment. But if you don't have money, you go to peer-to-peer model. What you need to sacrifice is the security. Okay, you want to implement security can, but maybe it's a bit harder because how are you going to um, um, even though you can authenticate, maybe this hacker, because he's willing to become one of the peer, willing to help the network, right? Even though he is a hacker, how do you know that he's a hacker? Maybe he can open an account as well, right? Okay, so there's difficulty in order to find out whether this person is um, has good intention or bad intention. We cannot know upfront. Okay, but there's an exception. You can have something like this. You can have a group of companies decided to share their information and use their computer as peer-to-peer. Okay, this one is all right because normally among companies, they don't do such thing. Okay, there's some kind of agreement. If you violate, you might be sued in court or something like that. So there's some kind of agreement in place to prevent everybody from doing hacking. That means you hack one another. Okay, so you can have that kind of agreement upfront. Okay, that means you share with different companies, let's say 100 or 200 or 1,000 companies. You share the resources, and everybody can share their file this way, in a more secure way. Okay, let's come back to this. So how do we do file sharing? Just now I talked at the higher level. That means the high level client and server, that's how we do distributed system. We share information or we give services using distributed system. How does the information is transmitted? Okay, there are two ways. Actually, there are three, not shown here. The first way is very obvious, is one-to-one, all right? Okay, so one-to-one communication, that means direct communication, just like what you see here. So this is one-to-one communication, okay, from client process A to database server. So this one-to-one. And this connection here, the communication here is private. That means between A and server, okay? That connection cannot be seen by client process B. So whatever that you share here is secure. Let's say you do any kind of transaction, it will be secure transaction if you are using a secure connection like HTTPS. There's another way to transmit your information. The other one of them is broadcast. Okay, broadcast is basically you want to tell everybody some information, so you broadcast. Okay, it's not so common in client and server. It might be quite common in peer-to-peer because when the new peer comes in, he doesn't know who is the higher rank, right? Maybe he has a broadcast. You ask everybody who is the leader. Okay, the leader of the group. That means the higher rank peer. Okay, so you have to broadcast this information to receive the information. Okay, so broadcast communication is for all receiver. Even though the receiver is not interested, you will have a copy of it. Okay, so broadcast normally you don't share, you don't transmit private information. Normally is asking for help. Okay, the other type of communication is multicast. So we got one-to-one, and then we got broadcast. The other one is multicast. Multicast is something like broadcast, except that you can look at it as a group-based kind of broadcast. So there's one group. For example here, this is the member of the group. So when a multicast is some kind of broadcasting, but then it broadcasts only to the member of that group only. Okay, so that's multicast. The one that is not a member will not be able to receive it. So this has a little bit of more security here. Okay, it might be used in peer-to-peer as well, because when I broadcast, normally I'll broadcast maybe to the one that near to me, because the one that is in the network, because he has been there for quite a while, he should know who is the leader. Okay, so I don't have to communicate directly with the leader. I just ask my neighbor, you have been there for quite some time, okay? Please tell me who is the leader, or who is the high rank community among this group here. Okay, so this guy, this node will be able to tell, okay, you're the newcomer, okay, this is the ID or the IP address of that the leader, okay, so that you can communicate with him. So this can be a multicast. It does not need to be a broadcast. Okay, so we have learned three things: one-to-one, multicast, and broadcast. I think you have learned this in your networking as well, just revision. Okay, just now I was talking about high level, medium level. Now we go a little bit lower level. Okay, how do we make the connection first? Okay, just now you already have the connection. That's why you can broadcast, you can do one-to-one, you can multicast. But how do you create the connection? Okay, you create the connection using this TCP/IP socket. Why is it called socket? It's just like the socket that you see on the wall here, like this kind of socket. Okay, that's why they gave a name socket. Okay, and the socket is one socket can have multiple ports. Okay, let's say for example I call this one socket, but I got multiple ports there. Okay, belonging to one socket. Right. So here is one socket, but it has many ports. This is another socket. It has multiple ports. And on one computer, you can create multiple sockets. Okay, so one socket for one private communication. Okay, you can create, if let's say it's a broadcast, that means this one socket here you can use for broadcast, you can use for multicast. But if it is one-to-one, then this socket has a private connection between one and the other. Okay. Now in one socket you can have multiple ports. Okay, you can have a lot of ports for that socket. So this port here is just like a sub connection. Okay, sub connection between these two. Let's say for example this IP address. So the IP address is one socket. Okay, and then it has port. This port is going to tell who actually is the receiver. So it's just like a sub communication line. Okay, one computer you got one IP, isn't it? Okay, but I can have multiple browsers running, right? If I don't have ports, if the signal comes in, the data that comes in, I do not know that data belongs to who, all right? So you need to differentiate that using port. Okay, so one browser maybe use one port, the other browser use another port. So when the data comes on to and fro, it knows where to go to. For example, when I receive on the same IP address, but looking at the port, I will know this belongs to this browser. Okay, so different browser will use different port. Okay, on the server, normally we have a fixed port number. Okay, let's say for example, FTP is a file transport protocol. It uses, if I'm not mistaken, port number 21. Okay, HTTP is also must be standard as well. Is 8080 or 8080. Okay, the common one. All right, and why do we need this fixed port? Let's say, for example, I want to go to Microsoft. Remember, I need the port so that it can recognize who to talk to, right? Which application to talk to. If let's say you don't use standard port number, how do I know that Microsoft, if I send, you'll go to the correct web server? because one computer can run multiple services, right? I can run maybe FTP, email, and web browser on the same computer using the same IP. Okay, but then if I want to connect to this server, how do I know that when I send, it goes to the web server or it goes to the email? So that needs to be fixed. Okay, so email has its own fixed port number. So that is fixed port, agreed upon port. Okay, we know that HTTP is 80, or 8080, 8080. FTP, I know there's 21. Email has its own port. Different kind of service has its own port number. Okay, on the server, on the client side, it's not fixed. Okay, when you get connected, you can ask for any free port. Okay, the fixed port is only at the server part because the client need to know for sure whenever it sends the request, it goes to the correct server. Okay, when I say server, it doesn't mean that the server run on different computer. It can be multiple server run on the same computer. Okay, and this server needs to service all the requests, and it needs to know which port so that the client, when it gets connected, it gets to the correct server on the same computer. Okay, so that is the socket and the ports. Okay, and the communication, they got two different types of communication. Once you establish the connection already, how do you transport the data? You can use UDP, which is unreliable kind of communication. We call UDP datagram. The other one is TCP. TCP is more, how to say, much larger, more heavier, and it is more reliable. Okay, what do I mean by that? If let's say you use UDP, you send the data, right? And halfway before it reaches the destination, something happened, it get corrupted or maybe it get dropped. The receiver receive, maybe it's corrupted or maybe it doesn't receive at all. Okay, and then that message is gone. Okay, and your program that sent do not know that the data is already missing. Okay, because UDP doesn't help the user or the program that use UDP. Okay, so that is unreliable kind of connection. But one thing is it's lightweight because it's simple to implement, and it's connectionless because when you send, you'll forget. You forget who this data packet is from or in which order. Okay, so that is UDP datagram. But if let's say you find out that this is not, maybe it's hard to use, you might switch to TCP. I'll go to TCP first before we get into the code. Okay, TCP is different. TCP is a string based, just now it's datagram based. That means packet by packet. We call datagram. They don't call packet, they call datagram, but it's, the meaning is the same. TCP is a string. That means the datagrams is assumed to be a stream of datagrams, and it has certain order. When you send, TCP send, it will give a number, 0, 1, 2, 3, so that when the receiver receive the datagram or the packets, it knows the order. Okay, which one comes first, which one comes later. Now you'll be wondering, why do we need to order them? Isn't that if I send 0 first, then send number 1? When the receiver receive, it should receive 0 and 1, right? But this is not always the case. For example, let's say this is a network. Let's say this is a router. Yeah, I don't want to use this, not to confuse you. This is a router or switches. Okay. Okay, this is A, this is B. All right. Now I can send my data this way. Maybe I'll use a different color. I can, let's say, okay, one thing about TCP is this, or any kind of protocol. Whenever you send data, you don't send one whole big chunk of data across. Let's say you have a video 1 gigabyte. You don't send one packet of 1 gigabyte. what do? The TCP will chop it down into smaller chunk. Okay, maybe 64K or less. So you got 1 gigabyte, let's say 1 gigabyte. You chop it down into 64K each. So each one of them is a packet or datagram, and then you send one by one. Okay, the reason why it does that is this: if I send the whole thing, the whole one gigabyte, that means you have to receive them 1 gigabyte before you acknowledge, right? But if I split it down into smaller chunk, smaller piece, if I send, if you receive it, you acknowledge. If you don't receive it, you also send a message back, negative acknowledgement, so that I know that piece or that segment or datagram is gone, so I can repeat sending them. Okay, so if I chop it down into smaller pieces, then it's easier to manage. I don't send the whole big 1 gigabyte. I chop it down into smaller pieces, and this one is called datagram or packets, data packets. Okay, these two terms is the same term. Now, because I got 1 gigabyte of file and I chop it down, if I send them in data packets, so I need to order them, right? Why do I need to number them or enumerate them? Because I cannot assume that whenever I send, I will only use one path. If you use this path, of course, it will be in order, because I send packet number 0, packet number 1, so they go in order, right? But the network doesn't work this way. Sometimes it will send this way, sometimes it will choose this way because this one is faster, and another moment it might choose this way, another moment it will choose this way, for example. And this has different delay. Sometimes you send first, but this one is slow. The second one, because it's slow, you start to use another path, and this one is fast. So when you receive, maybe packets number 3 arrive first, packet number 2 arrive later, right? If you don't put a number, then the receiver will think, okay, the one that arrived first will be the first part of the data, which is not right? So you have to put a number there, and that number is used by the TCP to make sure that first, there are two things. First thing is to know how you should order it, so that you can piece it back. Second thing is, it needs to tell the sender whether he has received or not. Okay, let's say for example, I received 0, 1, 4, 5, 6. Okay, I don't receive 3. If I notice that I don't receive 3, I would give a negative acknowledgement 3 to node A, so that node A knows that that packet is missing, and then it will send again. Okay, all this kind of hard work is done by TCP. You don't have to worry. You just tell TCP, I got 1 gigabyte of data to send, and you pass the TCP, the socket, and the socket will chop it down and then send to you, and it perform all this job for you. UDP is different. UDP, you have to chop it yourself, one thing, and then it doesn't handle this for you. That means when you send, if it is lost, it's your problem. Okay, you need to know how to react. That means the receiver needs to respond back, and this needs to be done by your program. Okay, because UDP do not have this kind of service for you. It is lightweight, it is very short, and is fast, but then all the maintenance, the management of the data that you transport is handled by your own. Okay, the reason why it is difficult is because the network have to send the data in packets, data packets. Okay, now if you ask this question, why not? Because we got a very fast network, right? Right now we are talking about petabyte per second, right? You know? But why the network still don't allow us to send one big chunk of file, still asking us to chop it down? Why? Because the network is shared network. Okay? Imagine that you send 1 gigabyte. That means that period of time of gigabyte that you send is only used by you. Everybody has to wait for you, right? If you chop it down, now you can share. So I can use, others also can use at the same time, so they don't have to wait for so long. Especially when you do video streaming. If you do video streaming, You don't stream the whole 1 gigabyte, right? You have to chop it down so that everybody share and everybody can receive the data, the video stream real time. Okay, so it is a must. And when I say 64 kilobyte here, it's not the TCP that enforce it, it's the network. The network will enforce it. If the network see that you transmit more than the number of byte is the maximum number of byte, you just drop it. That means when you send, it drop. You send, it drop. Okay. So the network will not cooperate with you if you violate it. So it's actually a protocol implemented inside the TCP/IP network itself. Okay. The limit you have to observe. But of course here, I mentioned it's 64. Actually, now they already expand it slightly bigger because we have a faster network. In the past, our network is very slow, so the maximum size is actually 64 kilobyte. But right now, it's bigger than that. But still, you have to chop it down into chunks. Okay, so what is the advantage? It's connection oriented. Connection oriented, that means when you get connected, it remembers. You remember who you are. You also remember the order. Okay, packet 0, packet 1, packet 2. If you miss, it will tell you. Okay, that means the protocol will tell its own self that the data is missing. And as a programmer, you don't have to worry. You just send and then you just forget about it. The TCP protocol will handle. If there's data drop, data missing, the TCP will handle it for you. It can retransmit for you. UDP, no, it's not data oriented, it's connectionless, meaning that if data is dropped and you cannot remember, you have to retransmit in your program. That means you yourself have as a programmer, you have to write the code to retransmit. Okay, so your task is a little bit harder. It's reliable because if data is missing, it will retransmit automatically. UDP, if it is missing, it's lost. Okay, if you don't retransmit, it's your problem. Okay, it doesn't help you. Okay, relatively high overhead because you have to keep a lot of information because TCP is connection oriented, so you have to remember who he is, how many, what segment or which data packets has been sent, which data packets has been acknowledged. So you have to remember all that. Okay, so it's relatively high in overhead, and it's only point to point. Okay, whereas UDP, it can be point to point. It can be unicast, which is something similar like multicast, except that is one to many. It can be broadcast. Okay, it is lightweight, it's unreliable. So which one to use? It depends on you. Okay, if you want reliability, you don't want to handle all the messy stuff like management, packet management, you use TCP. Okay, if you have your own management system in place, then you can opt for UDP. Okay. There's another thing that you want to use UDP rather than TCP. If you want to broadcast, you cannot use TCP. You have to use UDP. Okay, anything that multicast, broadcast, you have to use the UDP. There's no way for you to use TCP. So TCP is only for one point to point. That means one to one. Okay, if you want to use multicast, unicast, broadcast, you have to use UDP. Okay, this is a code how it is implemented. But unfortunately, we don't have this exercise in practical. Maybe in the past we have somebody remove it, because I remember I pitched this very long time ago. I remember it has this, but I don't see it anymore. Okay, nowadays I see it's all paracomputing. All this has been removed. But if you want to do distributed computing, you might want to use UDP and TCP. So how do you create a UDP server? This is a simple example. You have to use this this socket, Windows socket WS, and it's version 2, WS2, TCP/IP.h. If it is Linux, you just put socket. Okay, socket is the header. Okay, and then you have to import this library. Okay, you can do it this way using pragma, or you go to the command line, you type -f, and then WS2 _ 32 links. Okay, why do you need this? Because this is the library. Normally it is not, because it's not standard. So if it is not standard like IO string is standard, you don't have to include that library. But this is non-standard. you include it whenever you need it. So either you do it this way, or you go to the command line, you type -f ws2, exactly like what you see there. Then you will include this library into your program so that you can use the software. Okay, it's just like OMP. OMP is also not standard. When we want to use it, we have to, by right, we have to type in. We have to type like this as well, or because Visual Studio helped us. Visual Studio, when we click yes, remember we click yes. So when we click yes, the time it knows that it has to include OMP library. So it does that for us. We don't have to do it. Okay, so we don't have to do this. We don't have to type -f and all that. It's done by the Visual Studio. But if you use it in Linux, you have to write it. Okay. Okay, this namespace you all know, and this is just the version. We want to get the version. So we start up the Windows socket. We have to tell what version. We want version 2.2. Okay, we cannot start the Win socket. You will just print an error and then return. That means it will not continue. Okay, if it succeeded, that means you initialize the Windows socket. Now you create the socket. So you got 2 sockets to use. Okay, why do you need 2? Because you want to send and you want to receive. Okay. Sorry. Actually, you can send and receive in one socket. But here, because you're a server, you only want to receive. So you create the server, you call it in. Okay, the socket, you want to receive, and then you tell you want to use UDP. UDP is called socket datagram. Dgram means datagram. Okay. You don't type UDP. The name that they use, unfortunately, is called sock dgram, meaning that UDP. Okay. So AF INET means we want IPv4. Okay. So IPv4 UDP. So we create this socket using that protocol. Now, after that, we have to create the socket structure, or maybe the port. We need to initialize the port. So first thing is we have to use the IP address. Of course, you need to know the IP address. If you put address and you use what you can find, any address, any IP address. Okay, why any address? Because you can have Wi-Fi, you can internet, right? So if I put any address, you choose either one. Maybe the one that is active. Okay, and that will be the IP for my computer. Okay, so you choose one. Or if you don't want, you want to be specific, you want to use Wi-Fi, you go and find what is Wi-Fi IP address and you put it down. Okay. Okay, so the family is just what you see here. It's IPv4. You can use IPv6 as well, but here is IPv4 example. And then this is the port number. Okay, you can choose the port number. In this case, here, this server is not standard server. Okay, so we can choose any port number. So the port number is 54,000. Okay. Okay. There's one thing here that you see, HTONs. Okay, HTON is not HTON. It's actually host to network system. Okay. What it does is this. Our PC is little endian. x86 is little endian. You learned this before, right? Little endian and big endian. The order of the data that you put into the memory. If you little endian means the lower address is the lower digit. The higher address is the higher digit. Is it correct? Big endian is the reverse. The lower address is the higher digit. The higher address is the lower digit. Now, every computer, including the internet, is using big endian. Only x86 Intel decided to use little endian, try to be different. Okay, and some people like little endian, some people like big endian. So it depends on engineer. So it happens that Intel decided to use little endian in their computer, so it stays little endian. But the problem is, other computers like maybe if you talk about supercomputer, most of the supercomputer is using big endian, okay, or any other different computers like ARM. ARM is slightly different. ARM you can configure to be big endian or little endian. Okay, you can switch between these two. So ARM is a bit neutral in this. Okay, but if you talk about Apple computer in the past, Apple computer is using big endian. Okay, it uses a Motorola processor. Motorola processor is all big endian. Okay, so since the data is not the same order, one is using little endian, the network is using big endian. So when you send out the data, you need to reorder it. Okay, you have to reorder so that it becomes big endian. Okay, so what I mean is this: if I store this number 0x2345, this is lower byte, this is the upper byte, right? Okay, which one that we send first? If it is little endian, which one we send first? If we send in little endian, we send the lower address first. This one go first. Then only we send the upper byte, right? But if it is big endian, so this is little endian, LE. If big endian, okay, I send this one first. I send UB first, upper byte first. Then only I send lower byte. Okay? So imagine on the other side of the computer, because the network use big endian, so when you receive, it assumes that it's big endian. So it will think that this, you send upper byte first, then lower byte. But if you don't change it, because your computer is little endian, if you don't change it, you send lower byte first. So you think that this is upper byte, and you receive in the wrong order. That's the reason why we have to use this HTANs. This HTAN is host is your computer, to network system. So network system is big endian, and host depend on your computer. So this library will know that the current computer that you're using is Intel, so it knows that it's little endian, so it needs to swap it. Okay. Now, what happens if you are running old Apple computer? The old Apple computer run on Motorola processor. Motorola processor is big endian. Whenever you call this function, it just do nothing. Okay, because our Motorola computer is already big endian, so it doesn't need to swap it. Okay, but in Intel computer, this actually will swap. Okay, that's why Intel right now include in their instruction, the new instruction, which can do it in machine language. You just run in one instruction, it will change from little endian to big endian. Okay, so maybe this actually calls that function, use that instruction. Okay, once you already set up the socket, now you have to bind that socket to your system. Okay, once it bound, now it is activated. Okay, so if you fail to bind the socket, you will return the error and then you stop. Okay, if let's say it succeeded, you will proceed on, and then you start to wait. Okay, you can see here, receive from basically wait for the data to come. Okay, here actually zero memory is just you got buffer, right? The buffer has some data you zero it out. Okay, so that's why you see zero memory. Doesn't mean that you request for zero memory. No, you fill it in with zeros into the buffer, clear to zero. Okay, and then here you receive the data. You attempt to receive 1,000 bytes from the client. Okay, from any client that is created. Okay, and then whoever client that is connected, you will receive that client. And then if let's say there's any error, you get the last error and print it out and continue on. Okay, that means you wait for the next line. Okay, so basically that's it for this server, UDP server. Okay, if you want to close, okay, you have to close, right? If you don't close the socket is in use. If you try to run the program again, you tell you that socket is being used. Okay, you have to close, you have to shut down. Okay, shut down is just shut down the Windows socket. The more important one is the close socket. Okay, if you don't close, it is used, it's active. Okay, even though you don't use it, you have to return it so that when you use it next time, it's available for you to use. Okay, so that is UDP server. Now UDP client is more or less the same thing. It's just that right now what you do is you set the socket as up, okay, so that you can send, okay, you can send it to the external server. Okay, it's more or less the same. Just now it's receive from, this is send to. Okay, what do you send? You send this string here. There's some string there. Oh, it's not written. Yeah, here. Okay, the string comes from the user, argument 1. I'll show to you how to do this in the class later on. How to receive the data from the user command line interface. So you get the string from the user, and then this is a string. You change it to C string and then send, and this is the size of that string. Okay, you find it dynamically, and this is a server, the server that we create here. So where does it send to? It sends to itself. So your server is running on the same IP address. 127 is the local address. So you run your server on your local address, you run your client on local address as well. So when it sends, this one will use loopback, because when it see 127.0.0.0.1, it knows that this must be loopback. So it's sent, it does not go to the network, it comes back immediately into your server, to the port that you choose. This is the port, 54,000. Just now you choose 54,000 for the server, right? So it will connect to this server, 54,000, and is on the local host. Okay, and once it's sent, you find out whether it is any error. If there's any error, you print it out. Otherwise, you just close the socket. So basically, I have two programs. You can run this program. You have two programs running. You have to open up two command line interface, run the server, run the client. Now the server, when you run, you just listen. Okay, it will look like it is hanging, but actually it doesn't hang. It's just waiting. And then when you open up the second command line interface, you run this program, then you see on the other command console, you see the message that you type in. Okay, so you can send the message from one process. So these two command are two different processes. So you can send from one process to the other using UDP. So this is one example. Okay, I will not go into TCP. TCP is just the same like, what's TCP? There's none there. No TCP example. Okay, only UDP. TCP, I think you have to, yeah, there's none there. Okay, you have to go and find out yourself how to do TCP. Okay, the example that is shown here is only UDP. Okay, this activity for you to try. You can actually try this, right? Actually, maybe you have to make some changes a little bit in order to get it to work, but basically it's more or less working. Okay. If you want to try this and it doesn't work, you can always ask ChatGPT what's wrong. Okay, let's go back to this TCP. Now a lot of protocol use TCP. One of them is our web. Our web use TCP, HTTP or HTTPS. S stands for secure connection. So HTTPS is the one that we use always. And then FTP is the file transfer protocol. I think nobody uses it anymore, right? So, anybody here use FTP? Nobody uses. Everybody uses file sharing using web. Because everything is over the web right now, right? But in the past, when I was a student, we use all of them. We use HTTP, we use FTP. Even though our computer lab, we have FTP to get our file. Let's say lecturer want to share the file, they put into the FTP, okay, FTP server, and then we have to run FTP's client to receive the data, share the data. Okay, so that is in the past because we don't use HTTP to share data, but nowadays everything is HTTP. Okay, in the past we also use Telnet. I believe nowadays you don't use Telnet. Anybody here use Telnet? Telnet or SSH? SSH is secure version of Telnet. Nobody use. Anybody here learn IoT? Yeah, it's the same. Telnet is also the same. Telnet is not secure. SSH is secure. I see somebody here knows. How about the rest? Anybody here learn IoT before? Internet of Things. Nobody take Internet of Things here. Okay, if you learn Internet of Things, maybe you will learn SSSH. Because sometimes you need to connect to your Internet of Things. Alright, you need to connect using SSSH. Okay, so once you connect, you can control remotely. Okay, from your home, from any computer. Okay, so that's SSH. Yeah, I know. Now it's up already. Okay, I'll continue next week, and the code is 822 343.
툭툭.